Hello everyone. I'm pleased to present you this talk by myself, Pascal Sotin, a student at ENS Cantat-Vermande, and a colleague of mine, Hugues Cassé. This talk speaks of an analysis for data caches, and this analysis has a particularity to rely on a tool which counts some points in a set. First of all, I would like to emphasize the need for data cache analysis, and I present you a running example that I will use throughout the presentation. This code is a summation loop. It will trigger some cache misses due to the instruction cache. This kind of misses are quite well treated by the literature. Something which is a bit more tricky is the accesses to data. The scalar variables like sum, I, and n will probably be stored in registers. But the accesses to t, which occur once per iteration, can be either hits or misses. Misses will cost some execution time. And if you don't have a precise analysis, you must take some pessimism into account in your worst case execution time analysis, and maybe this will cause trouble when you are going to schedule. In this precise case, we should do something, because if we look at the memory, which I depicted on the bottom of the slide, we have some memory blocks, which are cache lines. And assuming that, for example, 4 cells of the array fits in one line, the first access to the block will be either hit or miss. It will be a hit if the array was already loaded, the cache, and a miss otherwise. But the 3 subsequent accesses must be hits, and so on. This is due to the regularity of this loop. The tool we are going to use as a backend is called Barvinock. It's a tool which takes as input a description of a set. This set is made of points having some integral coordinates. The tool is going to take this set, which is described by some linear constraints, meaning that it's a convex set, and it will return an arithmetic expression, which can be nonlinear. This expression can be either a number or some expression parameterized by some parameters. These parameters also appear in the problem. Solutions found by this tool are exact, and the tool finds them in polynomial time. The authors of the article, Verdulager and its colleagues, claim that this tool can be used for counting cache misses. It's not trivial, but that can be done, and that we pretend to do in this presentation. Before moving to our work, I would like to detail a little more this Barvinock tool and its potentiality. I illustrate 2 problems. In one problem we have a rectangle from which we remove a triangle, and we ask Barvinock to count the number of points within it. It says 9. In the second problem we've got a line, and using existentially quantified variable we can take a subset of this line, meaning the points which are multiple of 4. And Barvinock will tell us that the solution is 2. Barvinock is parametric. It means that we can adapt these problems, or we can have problems which have parameters. For example, if the rectangle is quite long, and arbitrarily long, we have some variable L which denotes its length. The solution provided by Barvinock is 3L. In the case of our line, if we have a line which is quite long, we don't know how long, then Barvinock will give us a bound which is a fraction of n, a fourth of n plus something. So I hope that you have in mind what can do this tool, and I hope that you have the intuition that it can count for us. Count, for example, cache misses. This is the whole idea of this presentation, on this work. We take a program and the material architecture. We turn that into a Barvinock problem, and Barvinock gives us a miss bound. The presentation has the following outline. First of all, we define precisely what we count. Then we present how do we derive a Barvinock problem from the program and its architecture. And in the third part, I will talk a bit more about cache modeling. How can we model the architecture in this framework? First of all, let's define what we count. The program I've shown you is some text, and we can give it some meaning using semantics. We are going to use a trace semantics, where the events we are tracking, the misses, appear. So first of all, we go to some control flow graph, where the instructions are carried by the edges. And in this control flow graph, we can find passes, which are going to be then executions. And these executions are also called traces. These executions are instrumented, and their transition can carry the event. So the red dot there is a cache miss. We are not considering a single trace, but any execution trace, and our analysis is going to provide, we wanted to provide, an upper bound on the number of misses in any execution trace. To do so, we are going to instrument the traces with loop counters. So we've got our loop. The loop head is marked by a triangle. It's the control point 1. And when we reach this control point from the outside, we initialize a counter to 0. And when we package to this control point, we increment this counter by 1. And this will decorate our traces. Now we rephrase our problem, and we want to know how many iterations are such that a miss may occur during this iteration. So you see that the problem now looks like some Barvinock problem. A limitation due to what we've done right now is that an iteration must now identify the event. So if we want to make an analysis, we can do it only for one memory access at a time. If we want to treat several memory accesses, we need to run the analysis several times. So that is what we count. Iterations where one specific miss can appear. Now let's look in detail how we are going to construct a problem such that if Barvinock solved it, we've got our miss bound. The idea of the work is going to relate the access at iteration n with the access at a previous iteration. So first of all, if there is no previous iteration, we just say that it's a miss. So there is now a 1 plus something. And the something is the number of iteration where we perform the body n-1 time. Then we perform the loop iteration once, and in the next loop iteration, the cache miss occur. Okay, so we split this question in two questions. First of all, reaching the loop head with n-1 as loop counter. This will be done using a summary that we don't compute in this work that we imagine it's provided. It's something rather simple. For example, it just said that I is the initial value of I0, is being incremented by n during n iteration, and capital N, the loop bound, is unchanged by the iteration, so it's preserved its initial value. So this is quite an easy part. The more tricky part is determining if a miss will occur not in the next iteration but the iteration after this one. To do that, we perform a backward analysis from the potential miss, and we derive a predicate which said that you may miss in the iteration of after this one if I is small enough to enter the loop twice, and if the block that you accessed in the current iteration is different from the one you will access in the iteration afterwards. So this formula can be computed with a backward analysis, and I will present you on the example how we can compute that. So we start from the point where the miss might occur, and we are going to reason with predicates which are sufficient condition for avoiding the miss. So if you are at location 2 in the iteration n, then to avoid the miss, the block must be in the cache. So it's the first line of my array. The age of the block, the maximal age of the block, is 0. I move backward to control point 1. Now, if my the age of the block I will access is still 0, then I can move to 2 safely. But alternatively, I can avoid the miss by not entering the loop. So I've got this disjunct which is added, which says that if I is greater or equal than n, then there will be no miss. I move a bit backward, the formula changes a little. I move once more backward. Now I face the transition between 3 and 2. And this transition is going to access the cache, and maybe it's going to give an age of 0 to the block that interests me. So the condition to have this age 0 will be that I access twice the same block. And eventually, we've got this condition. In order to avoid a miss, I must remain in the same block or not enter the loop. This is the precise negation of what we are going to use as may miss predicate. The backward analysis we used is quite familiar to most of you. It was proposed by Dijkstra. For an assignment, you just replace the value in the formula by the new value. For a guard, you add a conjunct, which is the condition. What is not going to be straightforward and what the paper details is the treatment of memory accesses. So we have some age function which maps to a block its maximal age, and we need to update this function. So updating a function is not something classical in the literature. We are going to consider that it's kind of a parallel update of an array, which would be the age. parallel updating is classical, but still it's a bit tricky because there we have an array with a number of cells which is quite variating. So let's assume that we built our condition, we built our problem and gave it to Barvinock. Barvinock, in this example, would give us the following bound. If we assume that a cache line is 16 bytes and an integer 4 bytes, so 4 integers per line. It will give us a bound which is parametric by n, parameterized by n. It will be something like a fourth of n, and it will be influenced by the position of t, the alignment of t, let's say. So this formula, we can give it to several, we can apply it with several parameters, and we've got the array on the grid on this slide, which is the blue cells. These cells indicates how many cache misses can occur with different values of n and different alignments of t. If we knew these values by advance, we could give these numbers to Barvinock, and Barvinock will give us numbers instead of formulas. The interest of formulas is that we understand a little the logic of the loop. Okay, so now we know how to build our problem, but there is still some details about how do we model the cache. So in what we've seen, we have been using an edge function, which is a function partially defined, which maps some blocks to their maximal age. Its treatment is that we represent this function as a logical formula in order to perform our weakest precondition calculus, and these formulas have been inspired by separation logic. The update function represents the behavior of the cache, how do cache block age. These update functions are represented by a list of pairs, value and condition. For example, the one we use in your trivial case is the following. If the block which is accessed is the block we update, then its age is 0. If the updated block is not the one accessed, then the age is anything. So we give an upper bound which is infinite. We can have something much more precise like that. This update function treats a cache which is associative by set. So the age can still become 0 if we access the block. The cache can remain the age can remain the same if we access a different block but in another set, or a different block but that doesn't make our block age due to associativity. So the associativity cannot be captured precisely with only a maximal age. We should introduce some minimal age to have a better treatment of that. In the other cases, the age is going to be increased by 1, and as long as we remain below the associativity, we can hope to prove some absence of misses. However, this definition, combined with the parallel assignment of the access treatment, is a potential combinatorial explosion. So we use SMT to discard many of the cases that appear. The more information we have about alignments, about placement in memory, the less this combinatorial explosion can appear. Okay, So this is the conclusion of my talk. I presented you a transformation that can input a program on an architecture that transform it into some Barvinock problem which deliver a misbound for some accesses in the program. The article contains more information. It's a bit more formal and gives some hints on the soundness of the approach. We apply the approach to other kind of programs, always small programs, but sometimes with multiple accesses, sometimes with if then else inside the loop, sometimes with nested loops. We give some information about the performances and discuss what can be traded in terms of precision to gain some computation time, even if the computation times for the example we have are not bad. And we give technical details for somebody who wants to implement itself the analysis. Okay, I hope you did enjoy the presentation, and please do not hesitate to read the paper and to write to me.